Okay, so we'll start with Chapter 1, which is on survival distributions and some characteristics of the life table. These are the references that I have used. And so this would be the chapters or the sections rather of this particular chapter. Okay, so I think I will discuss for this first lecture the first two sections. Okay, now let's begin with some notations. This notation here represents a person who's aged x, small x, okay? And we will use the capital X to denote a continuous random variable which represents the age at death of a newborn. Okay, so this would represent our newborn. So because of this, X is given this special name, the age at death of a newborn random variable. Okay, so this is the first of the random variables that we will encounter in this course. So capital X is a random variable, it's continuous, that represents the age at death of a newborn. So some functions associated with X would be the cumulative distribution function of this random variable X, and we all know that that is defined this way. So it's the probability that the random variable X is less than or equal to small x. And we will use this standard notation for the CDF of a random variable capital X evaluated at small x. So this probability actually gives us the probability that a newborn will die before attaining age small x. Will die on or before attaining age small x. Okay? And then we are more interested in the complement of that random variable x, of the CDF of this random variable x. This we will denote by small s of x. And clearly, small s of x would be equal to 1 minus the CDF of x evaluated at small x. Or in terms of probabilities, this would be the probability that the random variable capital X would be greater than small x. So this gives us the probability that a newborn will survive to age x. Okay? And because of this, we call this function the survival function of the random variable x. Okay? Now, let's try to illustrate how this random variable x can be used in terms of probability statements. Like, for instance, the first one, we want to find the probability that a newborn dies between ages small x of 1 and small x of 2. And number 2, we would like to find the conditional probability that a newborn will die between ages x of 1 and small x of 2 given survival to small x of 1. So to answer this, number 1 clearly can be represented this way, right? So that's the probability that the random variable x will be greater than small x of 1 and less than or equal to small x of 2. This now is the event that the newborn will die between ages x of 1 and x of 2. So in terms of the CDF of x, that can be expressed this way, right? The CDF of x evaluated at small x of 2 minus the CDF of x evaluated at small x of 1 is equal to, in terms of the survival function of x, to be the values, to be s of x of 1 minus s of x of 2. Okay, the second statement is a conditional probability, so we would have to use this representation for that probability statement. So it's the probability that a newborn dies between ages x of 1 and x of 2 given that he survives to age x of 1. So given capital X is greater than x of 1. So clearly that is equal to the following using how we define conditional probability. So that's the probability that x is greater than x of 1 and less than or equal to x of 2, intersection the probability that x is greater than x of 1, all over the probability that x is greater than x sub 1. But if you look at these two events, we can see that this event here is actually a subset of this event, right? This event is actually contained in this event. So their intersection will be the event that x is greater than x sub 1 and less or equal to x sub 2. Okay? So from our answer in question 1, this numerator is equal to this in terms of the survival function, while the denominator in terms of the CDF is equal to this, and the denominator in terms of the CDF is equal to this expression. So this probability in terms of the CDF of x is given by the following, right? And in terms of the survival function, it's going to be s of x sub 1 minus s of x sub 2 all over s of x sub 1 in terms of the survival function of the random variable x. Okay, now let's define another random variable which we will denote by t of x or simply by capital T, which denote the random variable representing the future lifetime of a person age x. So this time, our random variable is dependent on already a person who's already lived up to age x, and t of x would be the future lifetime of that person. Okay, and I think clearly that t is also going to be a continuous random variable like capital X. Having defined capital T this way, we call capital T the time until failure random variable, or the time until failure of a person aged x random variable. So we will just write it down as t, noting that this t is actually dependent on the age of x already. Okay? So the CDF of the CDF of t, which we will denote by capital G of t, gives us the probability that the random variable capital T is less than or equal to small t. So this gives us the probability that a person age x will die on or before attaining age x plus t. I always forget on or before, okay? Attaining age x plus t. This particular probability statement is given by the following symbol, TQX. So this is the probability that this gives us the probability that a person age X will die on or before attaining age X plus T. Or the probability that a person aged X will die within the next T periods of time. Okay? The complement of G of t, which is actually the probability that a person age x will survive to age x plus t, will give us or is represented by this notation, TPX. Okay? So TPX gives us the probability that a person age x will survive to age t. TQX is the probability that a person age x will die on or before age x plus t. So clearly, we can see that TPX plus TQX is always equal to 1. Okay? And we also note that if we relate the random variables x and t of 0 will actually just be x, right? This is the future lifetime of a newborn, and that's actually the random variable x. And so, if we write down this probability statement, so this is the probability that a newborn survives to age small x, that is actually just the survival function of the random variable x evaluated at small x. Okay? Now, let's have some probability statements regarding this random variable capital T. So number 1, we would like to get the probability that a newborn will survive to t years and die within the following u years. And the probability that a newborn will survive to age x plus t, then die before attaining age x plus t plus 1. Okay? So, the notation or the notation, this notation here gives us the probability or represents the following probability statement. The probability that a person age X will survive the next T years and die within the next few years. Okay? So in other words, what we want is the probability that T of X, note that the person is already age X, so we're getting the probability that T of X, or simply capital T, is greater than small t and less than or equal to T plus U. Right? So the person aged X will die within the next T, will survive for T years, and then die within the next few years. Okay? So in terms of the CDF of the random variable T, that would be G of T plus U minus G of T. And in terms of the survival function of the random variable T, that would be, sorry, the CDF of the random variable t in terms of our notation for q is given by the following. So these are the same. This gives us the probability that a person age x dies within the next t plus u years minus the probability that a person age x dies within the next t years. And that could be in terms of the survival function of the random variable t in this form, tpx minus t plus upx. And I think it's clear that that can be expressed. This probability here is actually equivalent to this statement. This statement tells us, or that this statement gives us the following: the probability that a person age x will survive for t years times the probability that a person age x plus t will die before, on or before attaining age x plus t plus u. Okay? Now, to answer question 2, it's a matter of replacing u here by 1, right? So, the probability that person age x will survive to age x plus t, then die before attaining age x plus t plus u is equal to this, or is represented by this representation. Take note that we did not write 1 anymore. We just wrote it as t bar qx. So this is the representation for the probability that a person age x will survive 40 years and then die within the next year. So using this particular statement, that we can express this as the probability that t is greater than small t and less than or equal to t plus 1. Or in terms of this representation, this is the same as tpx times qx plus t. Again, the u here is supposed to be 1, so we did not write it anymore. So in terms of this representation, this is tpx times qx plus t. So that would be the probability that a person age x will survive for t years, and then multiply that with the probability that a person age x plus t will die within the next year. Okay? Now, let's introduce another random variable, capital T, capital K, or k of x actually. This is a discrete random variable representing the complete future years lived by a person aged x. This is supposed to be, that should have that, okay? By a person aged x. That is, k of x is actually equal to the greatest integer value of t of x. Okay, the floor function of t of x. That's what it is also called. Okay, so we call this random variable k actually as the current future lifetime of a person aged x. Okay, so this is a discrete random variable. The probability mass function of k, right, is denoted by this. So that gives us the probability that t is greater than or equal to small k, and less than k plus 1, right? So in terms of the survival function of t, that would be equal to the following. So that's kpx minus k plus 1 px, or that's equal actually to this. This is the probability that a person age x will survive for k years times the probability that a person age x plus k will die within the next year. Or that is the same as this, k bar qx, where k is 0, 1, 2, and so on. Okay? By the way, we're assuming here, well, actually, k is discrete. It's not being assumed. It's given to be discrete. Okay? So, let's now relate the survival functions of the random variable x and t. So given the survival function of x, which we denoted by s of x, we note the following. We know that this is a continuous function in x and must be defined in this interval. X is greater than or equal to 0 and less than or equal to omega, where omega is called the limiting age. Okay, so clearly x cannot be negative, nor it can be bigger than omega, the limiting age. So we're assuming that everyone would have died before attaining, or the oldest person would be of age omega. And since this is the complement of the CDF of x, we know that this function, the survival function of x, must be a decreasing function, and that the value of s of 0 is equal to 1, and the value of s of omega is equal to 0. We note the following, that this notation, that this representation which gives us the probability that a newborn will survive to age x plus t is the same as this. The probability that a newborn will survive to age x times the probability that a person age x will survive for the next 3 years. Okay? And so, noting that this can be written out in terms of the survival function of x as well as this, we note that we can write down tpx as the survival function of x evaluated at x plus t all over the survival function of x evaluated at small x. Okay? And then, we can write it down also in terms, or rather tqx can be written now in terms of the survival function of x. Since we know that tqx is 1 minus tpx, and tpx is equal to this. So tqx in terms of the survival function of the random variable x is equal to this expression. So what we have here is the survival function of t expressed in terms of the survival function of x. Okay? Now, let's work on the following examples. Given that the survival function of x is as follows, it's equal to 1 minus x all over 105, where x is greater than or equal to 0 and less than or equal to 105. So clearly, 105 is omega. That's the limiting age. We want to find the following probabilities. Number 1, the probability that a newborn will survive to age 15. Number 2, the probability that a newborn will die between ages 15 and 42. Number 3, the probability that a life aged 15 will survive to age 42. And number 4, the probability that a life aged 15 will die before attaining age 42. Okay, so number 1, we would like to get the probability that a newborn will survive to age 15. So we can write it down in either of these two ways in terms of the survival function of t, which is 15p of 0, 15p0, or in terms of the survival function of x, which is s of 15. And we're given that directly to be 1 minus 15 all over 105, or that is actually 6 over 7. And then the next, number 2, we want to get the probability that a newborn will die between ages 15 and 42. So we're looking for a probability associated with the random variable x, because this is supposed to be a newborn. Given what we're given is a newborn. So we want to get the probability that capital X is greater than 15 and less than or equal to 42. So in terms of the survival function of x, that's s of 15 minus s of 42. So by direct substitution, that gives us 9 over 35 as a result. Okay? And then the probability that a life age 15 will survive to age 42 will be as follows, right? The probability that a person age 15 will survive to the next will survive for the next 27 years to reach age 42. Okay? So this can be written out in terms of the survival function of x to be s of 42 all over s of 15. Okay? And so by substitution, we get the result to be 7 over 10. And finally, the probability that a life age 15 will die before attaining age 42 is given by this. So that's 27q15, or that's the complement of 27p15. So that would be 3 over 10. Okay? Now, let me introduce the force of mortality. So, we note that x is a random variable, and the CDF for x is this. The PDF is given by this. And we are assuming, okay, that x is a random variable. So we know that the derivative of the CDF is actually equal to the PDF of x, assuming that x is a continuous random variable. So the derivative of the CDF of x is equal to the PDF of x. Okay, and we note that the derivative of capital F is defined this way. Okay, and let's look at the following. So we want to get the probability that a newborn will die between ages x and x plus delta x given survival to age small x. Okay, so from the discussion earlier, this is actually equal to this expression, right? That would be the CDF of x evaluated at x plus delta x minus the CDF of x evaluated at small x all over 1 minus the CDF of x evaluated at small x. But then we can rewrite it this way, right? So we multiplied by delta x the numerator and denominator and wrote it this way. Okay? And then we know that if we get the limit as delta x approach 0, this expression now is approximately equal to the following expression. Okay, the PDF of x times delta x all over 1 minus the CDF of x evaluated at small x. And this could be written out this way. In this form, this expression here is what this expression here gives the conditional PDF of x at exact age x given survival to age x. Okay, this conditional PDF is called the force of mortality, and this is denoted by mu of x. Okay, so the force of mortality is the conditional PDF of x at exact age x given survival to age x. Okay, so we defined in the previous slide the force of mortality to be equal to the PDF of x evaluated at small x all over the complement of the CDF of x. Okay? So that's how we define the force of mortality of at x. Okay? So this is the conditional PDF of x at exact age x, at exact age small x, given survival to age small x. Okay? If the the force of mortality is actually also called the failure rate or the hazard rate. Okay, we usually use the term force of mortality if our random variable x represents human lives, like what we're dealing with. Okay, but otherwise, if x do not represent human lives, it's usually referred to as failure rate or hazard rate. Okay, now let's consider the following. We note that if we get if we want to get the derivative of the survival function, okay, that would be the same as getting the derivative of 1 minus the CDF of x, right? Since the survival function of x is equal to 1 minus the CDF of x. But clearly, this would give us the negative of the derivative of the CDF of x evaluated at small x. And since x is a continuous random variable, then this expression here is actually equal to the negative of the PDF of x, evaluated at small x. So what we have here is the following. The derivative of the survival function of x is actually equal to the negative of the PDF of x. I think that's straightforward. So, the force of mortality, which we define this way, is actually the same as the negative of the derivative of the survival function of x all over the survival function of x, right? Since the PDF is equal to the negative of the derivative of the survival function, and the denominator here is actually the survival function. Okay? So the force of mortality in terms of the survival function of x is as follows. Okay? But I think it's clear that the following is true. We note that the survival function is a decreasing function. So the derivative of the survival function is always negative. And so the force of mortality is always a non-negative function. And s of x we know is also always greater than or equal to 0. Okay? Also, since this is nothing but the negative derivative of log of s of x with respect to x. By the way, whenever you see log, that means it's natural log. Okay? That's natural log. So the force of mortality is actually the same as the negative derivative of the natural log of s of x with respect to x, of course. Or we'll just call it log. When we say log, it means natural log. Okay? Now, what we want to do next is to find an expression for the PDF of x in terms of the force of mortality. Okay? So we know this already from the previous slide. The force of mortality of y is the same as the negative derivative of log of s of y with respect to y. So we can write that this way, right? So the negative mu of y dy is equal to d log of s of y. If we integrate both sides from x to x plus t, right? We're integrating both sides from x to x plus t. We get the following, right? So this integral and that operator d will cancel each other out. So we get log of s of x plus t minus log of s of x. And using the properties of log, this is the same as log of s of x plus t all over s of x, or that's the same as log of tpx. So what we're saying now is that log of tpx is equal to this definite integral. It's equal to negative the integral of mu of y dy, where y ranges from x to x plus t. Okay? Now look what happens. So we note that we can get the natural exponential of both sides, right? So doing that, so getting the natural exponential of both sides, we get the following form, right? So tpx is actually equal to e raised to negative of the integral of mu of y dy, where y ranges from x to x plus t. And then let's make some changes in our variable. Suppose s is equal to y plus x. So what happens now? So this y becomes x plus s. So you have mu sub x of s because of that. And then ds is equal to dy. So dy is replaced by ds. When y is equal to 0, when y is equal to x, s is 0. And when y is x plus t, s is t. So tpx is actually equal to e raised to negative the integral of mu sub x of s ds from 0 to t. So in this form, x is fixed, right? It's t which is varying. We're given already a person aged x, okay? So that x there is fixed. By the way, this mu sub x of x could also be written out as mu of x plus s. That's the same thing, okay? So tpx in terms of the force of mortality is equal to this expression, okay? Now, if we replace this x by 0 and replace this t by x, xp0, this now becomes xp0 is actually the survival function of s. Okay, so this t is replaced by x, this x is replaced by 0. So this 0, you don't have to write it down, so we can rewrite it this way. So it's e raised to the negative integral of mu of s ds from 0 to x, and that's the survival function. Okay, so the survival function of our random variable x in terms of the force of mortality is equal to this. Okay, this other form is the survival function of the random variable t in terms of the force of mortality. Okay, so it follows now that if we want to get the PDF of x, so we know that that's the same as the derivative of the CDF. That's the same as the derivative of 1 minus the survival function of x from the previous slide, so it should be the same as this. And in performing the operations here, you get to this part, right? That would be the negative of the derivative of e raised to this expression. So this is nothing but the derivative of e to the u, right? And so that would be e to the u times the derivative of u, okay? But then using the fundamental laws of calculus, this would just reduce to mu of x, right? This is just mu of x. And this, from the previous slide, is xp sub 0. Okay? So what we're saying now is that the PDF of x can be written out this way. It's xp0, the probability that a newborn will survive to age x, times the force of mortality evaluated at small x. By the way, this is actually just the survival function of x evaluated at small x, right? Yeah, I think it's here. Okay, so the PDF of x is the survival function of x evaluated at small x times the force of mortality evaluated at small x. Okay? Now, for the random variable t, so the CDF, the derivative of the CDF of t gives us the PDF of t. But we said that the CDF is TQX, so that's the same as the derivative with respect to t of TQX. But we note that TQX in terms of the survival function of t is equal to this. So if you're going to get the derivative of this with respect to t, you end up with this expression, right? So that would be the negative of the derivative of s of x plus t with respect to t all over s of x. We're differentiating with respect to t, so this would be constant. But then this expression here, we can rewrite it this way. And I think it's clear now that this is tpx, while this is mu sub x of t, or mu of x plus t, right? Or we can write it this way. By the way, mu is fixed, right? We're given the value of t, of x. So the PDF of t evaluated at small t is tpx times mu sub x of t. Okay? So that's the PDF of the random variable t. Okay, now let's uh, express now the survival functions in terms of the force of mortality. So the survival function of t, tpx, from a previous slide is given by the following, which reduces to this upon changing of the variable. Okay? We can express the survival function of x this way in terms of p, and from a previous slide also, it's written out this way. Okay? So the survival function of t and of x in terms of the force mortality is given by these expressions. Okay? This actually just summarizes what we have done in the previous slides. Okay? And I think I'll stop here. Then we'll continue with the next part in the next lecture. Okay?